In the last video, we looked at graphing the sine function. In this video, we're going to look at a very similar function called the cosine function. You'll notice that the cosine function is also periodic, meaning that it oscillates back and forth, repeating the same pattern over and over and over again. So for example, if we start at x equals 0, we complete the pattern or the cycle at 2 pi, and then we repeat the cycle afterward, and we keep doing that. So as we look at the parent function and its graph, we'll have again 5 key values, and the x values are the same as the values that we saw for the sine function, but this time the y values are different. We start with x equals 0 corresponding to a point off of the line of oscillation. And again, our line of oscillation is the x-axis, which is the equation y equals 0. The amount we deviate, or the distance we deviate from the line of oscillation, is the amplitude. Which is 1. And we've already stated that the period, the length of the cycle for it to repeat, is 2 pi. So if we want to graph cosine of pi x, we can again look at compressions and translations and reflections and stretches, just like we did for the sine function. So here we have our input x is multiplied by pi. So this corresponds to horizontal compression. We know it's a compression because pi is bigger than 1, and so that corresponds to the compression. If it were smaller than 1 in magnitude, then it would be a stretch. So therefore, that will affect the period. And the period originally is 2 pi, but it's getting scaled by a factor of pi. So therefore, the period is 2, which means that the increment is the period divided by 4. The amplitude has not changed. So let's go ahead and look at the graph. So looking at the parent function, we saw our 5 key values, and now what we see in our function is a change in the input. So we did not shift left or right, so our x value is still 0 to begin with. But now we have compressed, so our increment is 1/2. So therefore we can add 1/2 to our beginning value of 0. So 1/2, 1/2 plus another half is 1, 3/2, 2. And with the cosine function, we start off the line of oscillation, and we start above, then we go to the line of oscillation, down, back to the line of oscillation, and back to where we began. So let's mark off our x-axis with our increment. 0, 1/2, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves, 8 halves. Now we mark out where our y-axis is. That's where x is 0. And then our line of oscillation was not moved. We did not have a vertical shift, so it is still y equals 0, which is the x-axis. And the most we deviate from that is 1 unit. So we'll go away from our x-axis 1 unit. And now we will mark out our key points. With the cosine function, we start off of the line of oscillation, and then we go to the line of oscillation, and away, and back, ending where we began originally. And then we just continue the pattern. Now connecting with a nice smooth curve. No sharp turns. Then we go past where we end on both ends to make sure that we know that this continues forever in either direction. And so therefore the domain of this function is -infinity to infinity, and the range is -1 to 1. So we've said the period, we've said the amplitude, we've said the domain, we've said the range, and we have graphed. So now as we look at our next example, we see three things going on, three transformations. We have a negative, we have the 3, and then we have a -2. The negative means that we have a reflection about the x-axis. We have a vertical stretch, which that means that the amplitude is 3. So capital A would be -3, so its absolute value is 3. And amplitude is a distance, so it must not be negative. Now, the -2 is a vertical shift, and that vertical translation means that our line of oscillation is now y equals -2. So let's go ahead and look at what the period is. There was no compression or stretching horizontally, so the period is still 2 pi. The increment then would be the period divided by 4, so pi over 2. Now if we look at our parent function versus our function, we can go ahead and make our tables, and as we get more comfortable with this process, we may not need to do this, but that is up to you. So our original table of our parent function consisted of these 5 key points, and there was no horizontal change, no transformation on our x's, so those stay the same. But now what we have is a reflection, and we have a vertical stretch, and we have a vertical translation. So it might be easiest to go ahead and move that line of oscillation. So the line of oscillation consists of these points in our table. So we will now see those values move down 2 units. And now, if we go back to our y value of 1, we have reflected that, so it would be now at -1, but we've also stretched it vertically. So we will move it 3 points past our line of oscillation, below our line of oscillation in this case. Typically cosine starts above our line of oscillation, but because of the negative, we're going to be moving it below our line of oscillation, and we go 3 units below. Why 3 units? Because that's our amplitude. Now we will go 3 units above our line of oscillation, and then back to where we began. So now let's go ahead and graph these points. So our beginning value was 0, and then we had an increment of pi over 2. So pi over 2, pi is 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2. Find our y-axis. And now our line of oscillation is y equals -2. And then we need to go and make sure that we have values above that by 3 units and below that by 3 units. Now for a good baseline, I'm going to go ahead and sketch my line of oscillation. So we start off the line of oscillation, and because this cosine function has a negative coefficient, we will start below the line of oscillation. Then we move to the line of oscillation, and then on the other side of the line of oscillation by the magnitude of our amplitude. So we move 3 units away from our line of oscillation each time. And after the period, we should end up where we began, and then repeat the pattern. It's very easy, and I see students do this all the time, where they're paying too much attention to this x-axis and they end up putting a point on the x-axis. But in this case, my point vertically is independent of that x-axis in some sense. I'm looking at my amplitude as a distance away from the line of oscillation, not from the x-axis. So now let's connect the points with a nice smooth curve that has the shape of our parent function. And now we've said the amplitude, we've said the period, the domain is -infinity to infinity, and you'll see that the range here is a low of -5 all the way up to a +1. To begin our next example, what we will do is we will go ahead and rewrite our function so that we can see the transformations on the input more clearly. So here we have 2 transformations, both affecting our function horizontally. We have the 2 and we have the pi over 4. So the 2 is a horizontal compression, and a horizontal compression will affect the period. So the period originally is 2 pi, but it's being compressed by a factor of 2. we are subtracting pi over 4 from x, so that means that we're going to move our function's graph right pi over 4 units. And that would be, if you remember, what we call in trig a phase shift. So the amplitude did not change because there was no vertical stretching or compressing. So the amplitude is 1. And there was no vertical translation up or down. So the line of oscillation is still y equals 0. So as we look at our parent function and its key values, and we look at our function, we can go ahead and compare the tables. So our original table begins with 0 and increments by pi over 2. Starts off the line of oscillation. This time our inputs are changing, and our inputs have been shifted right. So we will begin with pi over 4. And then our increment is the period divided by 4. So we will increment by pi over 4. So we'll start with pi over 4 and we'll add pi over 4 to that. So we start with 1 pi over 4, 2 pi over 4, 3 pi over 4, 5 pi over 4, 6 pi over 4, till we have our 5 key values. Now, of course, we will simplify those x values whenever it comes to our final graph. Now, we did not have any change in our outputs, so those will remain the same. So let's go ahead and move toward the graph. So if we go ahead and start with our first value of pi over 4, and then move up by our increment, so pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 9 pi over 4. Now if we go and try to locate our y-axis, we'd have to look where x equals 0. But that is not on this number line. So we need to extend our number line to the left to ensure that we capture it. So we only have to move to the left pi over 4 units, and that will capture 0, which is indeed our y-axis. Our line of oscillation was y equals 0, and our amplitude was 1, so we just need to go up and down 1 unit from that line of oscillation. Now we started at pi over 4, and then we can put in our y value. So we start off the line of oscillation, and for the cosine we start above unless there's been a reflection, and then we move back and forth until we complete a period. And then we complete 2 periods by just continuing the cycle. And now, nice smooth curve. In this case, I can actually move to the left by repeating the pattern. I know that I'm going to pass through the origin. Now what we do see here is, I know that we've also did a compression, we've also done a compression, that is, But you can also see that a shift could make the cosine function into the sine function. So on your own, you might want to compare the graphs of y equals sine of x and y equals the cosine of x minus pi over 2.